I'll start in a couple of minutes. But just so before we start, there's material on like the main pages, but they also will link to here, which is let's see if I can get the ml@cl.github.io advds lectures. And then if you go on these, you can see there's quite extensive notes today. I won't cover everything in the lecture today because we've compressed a couple of lectures from last time. So I'll just see what's more natural to cover. And this is 2 years ago, the first lecture, which is going to be different this year. But when I'll do a recording here, I'll put it up there as well. So you'll get a recording of what I say this morning. So this is the Advanced Data Science course. And yeah, how are we doing? I'm going to give it another minute. So is everyone here who's not part 2 computer science? I don't know. It's not. Anyone else? Yeah. Did you say you're not part 2? Ah, okay. So week 4 already. Oh. Okay, we'll make a start. It's 5 past. So this is the Advanced Data Science course. And what we're going to try and do in this course is, so I need to put this on, take you on a bit of a journey of the what we think of as modern data science, which is a field that's changing quite rapidly because as technologies change. And so we'll try and capture some of that change, but also some of the ideas of how we structure approaches to that field. So you're going to be lectured by myself, Christian, and Carl Henrik. And I think the key thing about this field is it's a sort of emerging field. And one of the things I think about it is I've never seen it done well. I don't know anyone who's a good data scientist, but you can see it in places where it's done better. It's one of the big challenges of an emerging field because we just don't know how to do it really well yet. You could also argue the same thing about computer software, actually, but the situation's, I think, a little bit more extreme with data science because of a few reasons that I think we'll cover today. So the structure of the course is going to cover this data science landscape, a bit of background, and a structure that we're proposing that you use when you're doing data science. There are other structures. And to be clear, it's one we've made up, but hopefully you'll see that we're bringing quite a lot of good experience to this. Then I'll be doing this AI and data science lecture on Monday. Or was that Tuesday? Sorry, Monday. And then Christian will start talking about the sort of systems that we're using in data science and actually stuff that's related to the research work we do to try and improve the situation with data-driven decision-making in software systems, which is really where this all ends up being. And there's a lab session 1 and practical 1 are both released today. They're also on Moodle, so please have a look at them. The TIC session for lab session 1, I think, is the 7th of November. And then we're going to look at, Christian will look at AI deployment challenges, and then we'll start looking at some of the techniques we use. So those first bits are perhaps what you might not realize are really critical bits of data science. In fact, they're the biggest bits of data science if you do a data science job. But very often in universities, we just end up teaching here's some machine learning algorithms. But in most data science jobs, yes, you need to know those algorithms, but the deployment of those algorithms is only a small fraction of the work. So the assess and visualization lectures is where we start talking about how machine learning comes in. And it's certainly not a comprehensive course on machine learning. It's just going to try and teach you some exemplar algorithms that you can use. And then, in fact, that intro to statistical learning, these two I think are done by Carl Henrik, sorry, rather than me. These 2 lectures on statistical learning and generalized linear models. And the whole course is designed to feed into your assessment. So the assessment is due in, I think, 3rd of December. But what you'll see, and it's, I don't know, you'd have to ask someone like Radzim, who's one of the, who's giving us course support and has worked on the assessment, how challenging the assessment was. But what we tried to do is make the assessment easier by giving you pieces of work in the assignments, the lab classes, the checks that you're going to hand in that actually teach you how to do the assessment. Because you're quite compressed, right? We're only starting week 4. You're going to be handing in week 8. So this is quite a compressed course. So the whole point is that these lab classes support you in the assessment, right? And the things you're doing in the lab classes directly inform you about how to do the assessment. And so that's sort of week 7, we might have a summary lecture when we hand out the assessment. And then week 8 is the assessment handed. So the assessment, actually, I'm not sure how we're doing it, whether we're going to make it available to complete, as that's what we did in previous years, but people then turned out weren't doing that. So I think this year, the lab session, so sorry, this is from previous years and it's not quite accurate anymore. We've actually made the lab class much closer to the assessment than it was in previous years. Okay, so that's the sort of background to the course. You can read that also on Moodle. And since there's a lot to cover today, I want to move on reasonably quickly to give the context of what we're trying to say here and why. So I like to start with this sort of picture of what I think of as Henry Ford's faster horse. So this is a Model T car. And there's this quote that Henry Ford said. If he had been asked, if he had asked his customers what they wanted out of a car, they would have answered a faster horse. Now, actually, he never said this. It's like many apocryphal quotes, but it's a fun apocryphal quote because I like to use it when we think about things like AI. If I were to ask people what they want out of AI, is their answer a more intelligent human? And what does that even mean? I think it's an absurd concept. It makes no sense, actually. Our intelligence is intrinsically interlinked to who we are. And notions of artificial general intelligence are absurd. They're like artificial general horses. Makes no sense, right? The properties of a horse is an entity. Our intelligence is also a very complex entity, but it has particular characteristics. And while this course isn't so much about those, they affect the way we do data science, right? It has particular limitations. So a lot of my best description of those limitations is in this book, which was published last year. You don't have to read it, but I'll be referring to ideas that are in here. They're covered in the notes, called The Atomic Human. And the notion in this book is the following idea. So Democritus's atom is this story of if I have a piece of matter and I cut it in 2, and then I take one of the halves, and I cut that in 2, and I take one of the halves and I keep doing that. Does there become a point where I can no longer cut? And that's Democritus. It's a sort of philosophical idea. And of course, they were philosophers, so they didn't actually cut anything. They just thought about what it would be like to cut. And then they imagined, oh, there's probably a point where you can no longer cut, right? So if you think about computers, they're sort of things that are entering our cognitive space. And you can, machines in general, going back to the steam engine, when the steam engine was developed, people start saying, oh, wow, this is doing things, this has life force in it. The fire is giving life force. There's these works by Samuel Butler that talk about that. So ever since we've been automating human labor, you can see this as, in some sense, similar in terms of it's like we're cutting in to what we think of as uniquely human. We're cutting into ourselves cognitively, right, rather than physically. So every time the machine does something that we used to think was uniquely human, learns to play chess, can translate languages, can have a conversation, it's cutting something away, right? And then the question here is, well, is there an atomic human? Is there a place where you can't cut? And what is that thing? Because to me, this is a more interesting way to understand human intelligence. So that's the idea in the book. And in the first chapter, it says, yeah, there is a place that you can't cut. And I want to associate that with how that applies to our thinking about data analysis. Now, this quote, does anyone know who said this quote? It's apocryphally associated with several people. So 3 types of lies, damn lies, and statistics. Who apocryphally said that? So it's credited to Disraeli by Mark Twain, but I did a lot of digging into it, and it's where I found it was quoted was a gentleman called Arthur Balfour, who used to be prime minister, but was also foreign secretary. And he's actually quoting someone else when he says it. Now, what's interesting about this quote is it's from the late 19th century, right? It's from a period before modern statistics, before randomized controlled trials, before mechanisms were developed for us to try and make sure that statistics didn't mislead us. But there's something fascinating about the fact that statistics could mislead us, that our intelligence can be fooled by statistics, and that people can represent information in such a way that misleads, right? And that's kind of the aspect of our intelligence that I think is particularly important for what we're talking about today. So I'm going to try and describe what that is, because for me, it has this sort of consequence for today when it comes to data science. So that there's three types of lies, damn lies, and big data. That when we're looking at new types of data sets, and indeed when we're starting to work with computers and LLMs, we can be misled in a large number of ways. And the field of data science is in many respects trying to get on top of that. So if we look at what happened in mathematical statistics, so the initial field of statistics was called mathematical statistics because it was about proving when you could draw conclusions from data. So mathematical statistics, this is Carl Pearson, who's one of the sort of founders of mathematical statistics, worked at UCL. His mentor was someone called Francis Galton, who was a cousin of Darwin. And Carl Pearson and others such as Fisher and these people worked out under what circumstances we can draw conclusions from data by coming up with hypothesis testing, randomized controlled trials, things that we still use today to judge whether we should allow drugs to be sold for a particular purpose, or things that are being used on A/B testing, and things that are very commonly used in data science, key part of data science. So things that are used today to work out at scale what interface tweaks cause you to interact more with TikTok or Facebook. And actually through these very large randomized controlled trials, create very addictive interfaces that are plugging into you in ways that we can see as statistically valid, even if we don't know how they're operating with your intelligence, how they're infecting your intelligence. So we're sort of in this era where we have this need for something equivalent, mathematical data science, a set of techniques that allow us to understand when it's valid to draw the conclusions we're doing, because these conclusions can be very significant. They can be, particularly in statistics, they can drive multi-million-pound investments, right? Or they can drive the deployment of drugs to solve a particular disease, and very significant societal effects. And the shift I've seen in my career is going from piddling around with machine learning algorithms, which were of no consequence because they weren't on anyone's computer, they were just on your own computer, to these things being deployable to billions of computers in like an hour, right? Which is an extraordinary scientific effect. And why is this dangerous? Well, because what is the other piece of history that comes from this period that actually Carl Pearson and his mentor, Francis Galton in particular, is inextricably interlinked with? What emerged from that period? Eugenics. So these people who had these great scientific techniques that are the foundation of statistics today, the first and primary thing they used them for, Galton in particular, was trying to measure intelligence as if it was a unidimensional thing and trying to breed more intelligent British people to compete with German people. And it's a horrific story of oversimplification of the nature of human intelligence, driven by people who have some pretty cool mathematical tools. So when you see the parallels between that, and that's where the term general intelligence comes from, Spearman develops it in exactly that context. And what we're hearing today around notions of artificial general intelligence, just remember that is a eugenic term, okay? General intelligence is a eugenic term. It's a suggestion that you can measure intelligence in the same way you measure height. It's deeply problematic, right? We can measure height. We can't measure intelligence in that way. And so notions of artificial and general intelligence are very, very problematic when we think about how they will deploy. And you are the generation that's going to be involved in their deployment. That's not the main focus of this course, because actually what we're more interested in is perhaps the more practical domain of what it means to draw conclusions from data. But you could be manipulated in the same way when you're trying to draw conclusions of data as you can be by these very simple ideas coming from people who have a very shallow understanding of the nature of intelligence. So the first thing I'm going to try and do is give you an understanding of why your intelligence is very, very special and particular to you from a sort of scientific perspective. So what thing remains? Well, the story I want to tell you about is by a gentleman called Jean-Dominique Bauby, who wrote a book called The Diving Bell and the Butterfly. And the book, has anyone seen this? It was a film as well. So the book is about his autobiography. But the remarkable thing about his autobiography is he became locked in. He was paralyzed. So he had a brainstem stroke in 1995. He was the French editor of, I think, Elle or Vogue or one of these magazines. And he lost the ability to move. So he lost his ability to communicate vocally. The only thing he could do was wink. And the remarkable thing about his book is he wrote the book after he became locked in. So this book was written from this state, and it's called The Diving Bell and the Butterfly. It's written in French. He was French, and it's actually called Le Scaphandre et les Papillons. Sorry for my pronunciation for those who speak French. That means diving suit and butterfly, not diving bell. And what he's describing is the difference between how he feels in his mind and his ability to imagine and see the future, the butterfly, and how he feels physically in terms of the constraints that he's, you know, the diving suit, as in, it's the type of diving suit, I don't know if people still read Tintin and Red Rackham's Treasure, but these ancient diving suits where people plod around on the bottom of the sea with a tube to breathe through. And his notion is his only way of communicating with the outside world is to pull on this tube. And he wrote the book by pulling on this tube. So his assistant pointed at letters on a page and he winked because one of his eyes, I mean, it's actually sort of the motion of your eyes, you know, and this is why sort of Stephen Hawking, who also, as in the sense, was locked in, can still move their eyes. Your eyes are controlled not through the brainstem, what was destroyed, they're controlled through other mechanisms. So that's why you often have eye movement if you have these locked-in syndromes. And the remarkable thing, so he writes this book after he becomes locked in. And the thing about that is people are fascinated by that state, right? It took him 10 months, 4 hours a day to write this book. And I think whenever we think, what would it be like to be in that state? We just can't imagine it. And that's a bit strange because you are all in that state. That is the state of your intelligence, right? You're not locked in to the same extent as Jean-Dominique Bauby, but what we're interested in here is comparing to the machine, the computer, right? Not other humans. And it turns out that in comparison to the computer, you are utterly locked in. So how can we measure that? Well, this gentleman here, Claude Shannon, he's did a lot of work on information theory, and he developed the notion of information theory as a measurable, excuse me. So unlike intelligence, which is not measurable and not rankable, we can talk about quantities of information because Shannon defined it very rigorously. And of course, his definitions turn out to be extremely important. You know, even in physics, some people say that information is more fundamental than energy. I don't know the arguments around that, but it's a really fundamental concept. And you'll have seen it in other courses. There's an information theory course, I think, in this year, if you choose to take it. But he's quantifying information in terms of bits, where a bit of information is the amount of information you get if I give you the result of a 50-50 coin toss, right? Or if I tell you the result of Federer versus Nadal in a tennis match when the odds were 50-50. That's the key point. Doesn't matter what the context was. That's Shannon's big innovation, right? That the context is removed. It's very closely related to thermodynamics, information theory, and entropy. But in entropy, they always talk about the context. In information theory, you don't. You just talk about probability distributions. So what's interesting is we can look at the rate of communication that Bauby was doing in bits per minute. Apologies, I've lost the image there. That should be a picture of Bauby. And we can say if he was it took him 10 months, 4 hours a day. I counted the number of words in the translation, the English book, and it turns out the average amount of information in an English word is 12 bits. So it looks like he's communicating, from my calculations, at around 6 bits of information per minute. That's his communication rate, which is quite a lot slower than ours, because me talking to you now, I'm going a bit quick because there's a lot to fit in. Apologies for that. There'll be a video though. Talking to you now, probably 150, 200 words per minute. So let's say it's about it's about 300 times faster than Bobby because he's going half a word a minute, right? So I'm saying 2000 bits a minute. I mean, these are best estimates. They only need to be best estimates because, of course, what rates do computers communicate at in bits per minute with modern Ethernet? What's modern Ethernet nowadays? 10 gig, yeah. So let's take 10 gig. So 10 gig is 600 billion bits per minute. So I was going fast, but I'll go slow there. The difference between us and Bobby, factor of 300. So that's the difference between walking pace and speed of sound. The difference between us and the machine, we're already speed of sound, is the difference between walking space and speed of what? Light. Kind of mind-blowing. And why does that happen? Well, interestingly, there's two factors there. There's a physical factor. I'm communicating with you using sound waves. What's the difference between sound speed and speed of light? It's a million factor, right? So there's already a factor of a million there. If I'm using the same coding system for sound and light, the information will travel a million times faster over the light wave coding than the sound coding. Interestingly, we've put a lot of effort into how we're coding this stuff. That's what computer scientists have done. And our communication through sound is not optimized for compression of information. It's actually, there's robustness issues, there's a noisy channel, everything else like that. So it turns out there's an additional factor of 300 that comes from clever engineering around the coding. So the difference between me speaking and me speaking to you, two computers communicating, factor of 300 million. So if you have access to 300 million times more information, do you think your intelligence is going to operate in the same way? Absolutely not. Absolutely not. And so any notions you have of the machine as doing anything like human intelligence are absurd and ridiculous. It, of course, can emulate things that humans do, but even the way it does that is very, very different from the way we do these things, okay? So that's really, really important. And then to me, that's the first point about the atomic human. That what is the thing that the machine cannot have? It's our limitations, our weaknesses, and as I'll come to in a minute, our vulnerabilities. So we are special, not because of capabilities, but because of capabilities layered on top of limitations, right? Because how we overcome this limitation is totally extraordinary. How societies work, how humans communicate between each other, how we collaborate to do things, despite this extraordinary limitation on the bandwidth, is just, that's the sophistication of society. All the stuff that humanities and social scientists people care about, and we often don't think about. But when you're starting to do data science in the current world, and it's having a significant effect on society, you need to think about it again, yeah? So basically, the machine is 300 million times faster than us, and that has a particular effect on the way we communicate with each other. So in order to share information with other human beings through this sort of really narrow bandwidth, of course, inside we're communicating almost speed of light because we're using neurons. I mean, some fraction because there's synaptic gaps between the neurons. We don't propagate quite at the speed of light, but it's up there somewhere, right? So the reason you have a sense of self is because internally you're communicating with electricity, right? And therefore things are moving around in milliseconds and whatever else, and everything feels like it's one, even though the cells are independent. You have a sense you are one. It comes from your brain because your brain is wired up to everything else. And then, of course, you don't have that sense across other people. Otherwise, we would be the what? The Borg. Yes, come on, Star Trek, right? If we were wired up to other people, we would have a shared, we would just be a sensor network, right? Rather than, and we are the opposite of a sensor network. When we build a sensor network, we're thinking about distributed things with high bandwidth communication between them, very little compute on the nodes. Our architecture, utterly different, very low bandwidth interconnection, massive compute on the nodes. No one would ever build an architecture like this today because we can already use electromagnetic radiation to communicate, right? Unless you start looking at deep space architectures or things like that, for anyone who likes watching The Expanse or the book. So how do we communicate with each other? Well, the first thing I have to do is I put a lot of computational effort, because I have a big brain, you have a big brain, we all have big brains, very powerful brains, into deciding what to say, right? So I have a model in my head of who you are. I'm trying to use examples like the Borg or whatever else. that is based on the fact that I'm speaking to computer scientists. And I suspect some of you watch Star Trek. You know, that may be not true because I'm 53 and, you know, you're young, so everything changes over time, right? That's why generational communication doesn't work so well. But I have a base sense of who humans are and what they're like. And that's there consciously and subconsciously. So some of those decisions are conscious and some of them are just intuitive, right? And then when I use that, I choose what I say based on my knowledge that I'm speaking to other human beings. And then, of course, when you're listening, you have a model in your head of who you think I am, and also who you think that you are. And I think, you know, psychology studies show that we can do this to a depth of 3 or something, right? Something like that, of modeling the fact that you're modeling who I am and I'm modeling who you are. Of course, that becomes an infinite recursion, and you can't computationally deal with that. So there's some limit at which it becomes pointless, presumably. Certainly, if we were done, I mean, the nice thing about being computer scientists, you can think about how are you going to design for this ecosystem when you're a computer scientist, right? And that's kind of what's driving this thinking. So you know what I mean? Oh, yeah, you have to do some recursion. Oh, but you can't keep doing it, right? So then you absorb what you're saying, you combine it with your understanding of who I am, and then you choose to say something that is almost like a reaction to that, sort of saying, no, can I just clarify this? Or I want to do that if we're having a conversation. I mean, this is one way at the moment, but if we were having a conversation. And then I assimilate that. And then on the basis of that, I say something back. Now, if this works well, it's the most extraordinary, beautiful thing. And it isn't based just on modeling each other. It's based on shared cultural perceptions, shared knowledge of what it means to be a human being, shared sense of what it means to be a computer scientist, if you're talking to another computer scientist, or a student at Cambridge, or if you're talking to someone from your country, a fellow country person, because different countries have different cultures. And these cultures allow us to talk about these concepts, whatever the equivalent concept is, whether it's the Borg, whether it's something coming from a religious background, or whatever it is, to communicate very sophisticated ideas, because we know the concept, right? And we can say it's a bit like that, right? And a lot of those concepts relate to human interaction with the world. When it works, it's absolutely beautiful. And when it doesn't work, we end up arguing with each other. And those arguments are often triggered when there's a mismatch between cultural understanding. That's very common. So if a machine learning person's talking to a statistician, there's a slight mismatch, and slight mismatches are particularly problematic. If there's a big mismatch, you very quickly get you don't understand each other and back off. If there's a slight mismatch, you're really confused about why they're going in this odd direction. And that often happens in your community. For example, machine learners and statisticians use all the same maths, broadly trying to do the same thing, apart from a statistician has at the core that they want to prove something on the basis of the data. The machine learner is typically trying to predict things, or that's how it was in the past. So you make different design decisions because you've got this slightly different origin. And if you don't understand that, then you say, why the hell are you doing that? Well, they're trying to achieve something different, right? They're going in a different place. Now, this notion of how we represent is even, so there's this cool thing that you can play this video from 1940s. It's a psychology text, which is about how we will, even if they are animated correctly, associate, I'll just play it while I'm talking, associate objects with emotions. So these are just triangles and circles. And this is obviously the period of, you know, animation in cinemas and whatever else. So scientists they're doing this sort of film, and they asked several subjects, only about 5 or 6. The paper itself, you know, wouldn't pass muster today because there's too few people, about what are these triangles and circles experiencing. And you can give them fairly consistent emotional stories about what's going on that are actually based on analogous concepts or ways of acting. And of course, what's going on there is the animator has in their mind something that they're trying to express, and they're trying to express it through this channel of these interacting objects. But one of the things that's interesting that Haider then goes to talk on about in his interpersonal communication book is he's saying that in order to have that interaction with something, these entities have to be psychologically represented in your mind. Now, I don't know, I mean, this is a loose concept. We don't know exactly what that looks like. But the notion of psychological representation becomes important when we're thinking about that communication before. If I'm going to communicate with something, I need to psychologically represent it. Now, it just gets angry and destroys everything now. I mean, so that's my interpretation. You're entitled to your own objective interpretation. Do that. Now what are we watching? cool 1 hour smoke visual loop. Nice. Let's do that for the rest of the lecture. Okay, so what's that got to do with our situation? Well, when it comes to the computer, what on earth is going on? In order to interact with the computer, we end up psychologically representing the computer in our minds. And what is our best and closest approximation model that we use for this? Well, we don't really have a good understanding, even view as computer scientists, of how the computer's doing things. So we do something that is very, very common that you'll see constantly in human beings. We anthropomorphize, right? So we tend to think of the entity we're communicating as human-like, even if it's not human, even if it's communicating at a rate 300 million times faster, right? So it's nothing to do with us. And it actually can't interact with the world in the way that we interact with the world. So it gets this information in an utterly different way. So you get this old phenomena, which, you know, we'll move beyond this, but this is the sort of world before LLMs. You try saying a few things to the computer with your model of what it's doing, and then what happens? Well, computer says no, and you end up swearing at it, because that's everyone's experience, including you as computer scientists, of interfacing with machines, because it doesn't see the world in the same way as us. It doesn't have that cultural context. It doesn't have those shared ideas. That means it has a sense of the words we're using. Well, it didn't have, but we'll come back to that. Okay, so this is leading to this very evolved relationship with information. It's the heart of what data science is about, right? So the new flow of information is the following. So lies, damn lies, and statistics is exploiting, in effect, something, or I mean, I don't know the psychological details, the best way of talking about it, but it's an effect that, like, if you're trying to interact with data, you tend to overinterpret, because data is an odd thing the way it's presented in statistics. You're just given a table of data, but your brain is used to intervening on the world, right? Going around and doing things. So your intelligence is this sort of like searching for something, and then, you know, you poke it to see what it does. And that's because your intelligence is a motor intelligence. The very earliest animals just were sensory motor systems, sense and respond. So at your lowest level, your intelligence is still that, right? You know, that you've got this bit of your intelligence that is integrated with the world, whether it's your ability to do sort of things like allow a cup to slip in your fingers, which is really extraordinary. We can't get that in, you know, computer systems at the moment, just allowing friction breaking. And that implies there's computation going on in the fingertips. There's also computation going on in the spine. There's computation going on in the brainstem. And the bit you're aware of is mainly as the neocortex, and even that, I think some of it you're not aware of, right? But the prefrontal cortex for planning, the visual cortex at the rear, these pieces of your mind that do not exist on other animals like lizards, right? Or in birds, just have a totally different structure in birds. But these animals can still do all these motor things, extraordinary motor things like what a lizard will do. And so much of our intelligence is in that area. And it's an interactive intelligence. So when we're presented with something static, we tend to make the mistake of overinterpreting it, doing some sort of anthropomorphization, seeing things that aren't there. And that's why you get lies, damn lies, and statistics. And that's why you end up with classical statistics coming in. But the key challenge we're now facing is the following, that the machine is presenting a new channel for manipulation. And it's a new channel because the bandwidth of communication between the machine and data is 300 million times greater. I couldn't draw it even logarithmically, right? Well, maybe that is roughly right, logarithmically, 10 times larger than our ability to interact with the machine. So what you end up with is this lies, damn lies, and big data that is characterized by the new flow of information coming this way, that the machine is seeing vast quantities of data, often personal data, certainly in the case of social media. It can work out exactly how we respond by doing randomized controlled trials on us using classical statistics. And it can feed us with a world that kind of is a world that we will react to at some base level that is below our sort of very, what one would call sort of slower intelligence, but is fitting in with things that are fundamental to who we are as human beings, like social validation, or the urge to have our biases confirmed. It's just found all those sort of things through this relationship. And of course, as data scientists, you know, you're faced with being the people that have to unpick that, or you're going to be asked to be the people that exploit that to make a project make more money, because we don't have the equivalent of mathematical data science. So where does AI fit into this? Well, we'll come back to that again, but it's, you know, it's a big thing what's going on with AI, but broadly speaking, I sort of almost see AI as a subfield of data science for the context of this lecture, right? This stuff that's going on here is computer science or database systems, and that's why you'll see that you're going to be doing quite a lot of that, whereas this stuff here is about, well, how do we interact? It's sort of almost HCI or things like that, yeah? There's a bunch of that going on here, visualization, things like that. So how do we approach this? Well, the first model I want you to think about is what I think of as data science as debugging. The first problem that computer scientists have with data science is because it involves coding, they think of it like programming, and it's nothing to do with programming, right? What do I mean it's like debugging? It's because it's like the following thing. If I give you, imagine you are an operational software engineer working for a company, and I come along and I give you a USB stick and I say, there's a library of code on this USB stick. No idea who wrote it, where it came from, but there's an API call you can make that will deliver a significant lift for our business, that will make us money. There's an API call on this. I don't know what one it is. What are you going to do as a software engineer? And please integrate it. What are you going to do as a software engineer? Say, no, that's crazy. That's going to leave us vulnerable to all sorts of cyber risk. We have no idea what could go wrong in this, what the code's written and where it's coming from. What if I even tell you, oh, and by the way, someone's got access to this code. It's going to change over time. Oh my God, it's the stupidest idea ever from a computer science point of view. But what am I describing to you? Integration of data sets into software systems. Because the models you're using, whether that's PCA, whether that's logistic regression, whether that's a deep neural network, whether that's whatever, are just API calls to the data, right? They're just different API calls you can try on the data, because there's information in the data, and the way to get the information out is to use machine learning. But how are you going to integrate that? Well, how would you integrate it if it was a software library? Enormous amounts of debugging, enormous amounts of debugging. At the end of your project, once you delivered it, there might be just one line that is the right API call as far as you can judge, yeah? One line to say, this was the API call that gave us the lift. But all the thought that wants to go in there to sort of understand why that was the right API call to ship is an enormous amount of work, right? More work than you've put into any line of code you've ever written before, because it had to exhaustively explore what could go wrong. It has a bunch of safety checks around it to make sure the API call is continuing to work as it worked at the moment you called it, right? And the big problem we have here is that entire journey of that debugging story that you created. How do we record and share our debugging stories in software engineering? We don't. We do them on our own, and then we bury them pretending they never happened, right? And there are some good techniques we can use. But the big problem here is this can't be buried, because later on, some other data scientist is going to come along and look at that API call and think, why isn't that working? Why have they made that choice? And they want to see the story and the narrative of everything you thought through that caused you to end up on that API. And that currently isn't embedded in the code. So what you'll see your assignment is to build that story, right? So when it comes to your assignment, you'll be doing a bunch of the stuff you need to do, but you'll be telling the story, right? The end of your assignment, you know, there's a load of boilerplate code, database calls, all this sort of crap that you have to do when you're doing data science, some sort of processing. But basically, you know, it's effectively a line of code with all these bits and pieces in between. So this is the challenge that anecdotally, for any given challenge, and I think it's actually worse than this, 80% of time is spent on wrangling and 20% of time spent on modeling. And that's why we're in a big problem, because people aren't teaching this wrangling piece, and people end up being recruited as machine learning engineers to do jobs that involve serious data wrangling. And the ecosystems within companies are not up to speed in terms of understanding how to record this data wrangling and share it. So it's often these notebooks that you'll create, they often just reside on an individual data scientist's computer, forgotten forever, or accessible only if that person's still in the company and they have a good file storage system. So just worried about. So I'm just going to land on the last piece. And as I said, there's a lot more here than you have to. I'm giving you a sort of sense of the thing. You can feel free to go through the notes. And their notes, they sort of cobble together things. So don't worry too much. But there's references in here. I'm just trying to give you the sense of what's going on. So how are we trying to address that for you? Well, there are, as I said, no perfect ways of doing data science. So we've got a framework that we're asking you to use to support you in going through this. And it's called the Fynesse framework. And it's got these 3 stages: access, assess, and address. So there are other data science frameworks. This is the CRISP data mining framework, but it's quite old. It's from like 2006. So oddly, this is written, at a time when we're still working out how to do software as a service. So you can see these little pieces that are actually, there's still, all this is in some sense interesting and valid. It's not what we're teaching you, because we're trying to teach you something that is helpful for the individual data scientist and should be helpful for the company going after that. But, these are all important points: business understanding, data preparation, modeling, evaluation, deployment, and everything going in a circle, right? These big circles. This is all true. It's not the framework we're teaching. It's called the CRISP data mining framework. I love this quote. And now you see why I've emphasized the human in this. This is Cathy O'Neill, who also wrote Weapons of Math Destruction, this book, but she wrote this O'Reilly book on data science. More generally, a data scientist is someone who knows how to extract meaning from and interpret data, which requires both tools and methods from statistics and machine learning, as well as being human. It requires being human. She spends a lot of time in the process of collecting, cleaning, and munging data, because data is never clean. This process requires persistence, statistics, and software engineering skills that are also necessary for understanding biases in the data and for debugging logging output from the code. So the data scientist today has to do everything. There is no separation of concerns. And this is why it isn't being done well, because the societal effect of these things is significant. And if the data scientists themselves isn't a human and being aware of that, very damaging things are deployed. And that's the world we're living in at the moment, where they have been deployed. Whether that's for online harms, things like child sex abuse, or just the nature of modern social media and its divisiveness and the way it undermines democracy, right? It wasn't like that an individual knew this when they deployed it, by the way. But, we have to be aware of it. Here's their example. That's from their book, the O'Neill and Strutt book, about what they think. I also think about it in this cycle way. So I'm not going to talk too much about this, but this constant need to experiment, analyze, design, and going around and around in a circle. It's never ending because everything's fluid, because the data's changing, right? And so this becomes so important that you are a scientist. This is a scientific workflow, right? That you have to be aware that things are changing underneath. So the final thing that I want to sort of say is the pieces of this framework. So there's 3 aspects to the framework that we think that you should be using. And they are the following: 3 stages. Now, again, there's cycling, and there's going back up and down these stages. These stages go forward in some sense, but because of all those cycles, they don't always go forward, and we often refine what goes where. So it's the access, assess, address framework. And the basic idea is the following: that the first thing you need to do is get hold of the damn data. And even that is hard. So a lot of data science projects fail because someone believes that they have the data, but they've never even looked or checked. So I call that hearsay data, because they hear they got the data and they say it's there. But if the data has never been used in a previous framework, it's unlikely to be any quality. Companies think data is their secret sauce, but if no one's ever tasted the sauce will be rancid, right? So that's the access stage, actually getting to look at the data and electronically load it in, right? So because the data could be in multiple different formats. So we'll come to an example in a bit where the data is written in logbooks, right? Handwritten in logbooks. Or it could be distributed across multiple mobile phones. Or it could be, in the case you'll look at for your access, it's online in a government database, and you need to pull it down to get access to it, to play with it. So that's the access stage. Access can also involve legal and ethical challenges. Do you have the rights to access the data? even if you legally have the rights, should you be using this data in, because the problem is with technology changes, law is behind ethical decision-making. In a stable environment, law and ethics have had time to converge to some extent. They're not completely overlapping. But when technologies change, the law can be a long way behind ethical decision-making, right? And, and even if you are in a company, companies care about what their customers think. So they're trying to operate ethically, one hopes. Some of them, most of them maybe. Assess is a different stage. So imagine the data is now on your machine, but you don't know what you're going to do with it. No one said we're going to predict this or understand that yet. But there's a bunch of work you can do to characterize that data. Does it have missing values? If there are missing values, how are they coded? How was it recorded? What does each column mean? What's the schema for the data? All of these things. And the reason we separate this out is because this work is all reusable, right? One of the challenges was something called the software crisis. And I mean, if you don't know it, look it up. And the characterization of the software crisis is it became easier to write software. People wrote more and more software. And there became too much software for anyone to handle. And one of the analyses that they suggested is the problem was that the code that was being written wasn't reusable. So everyone's then rewriting their own code to do the same thing. So you're not building on top of other code. So object-oriented programming, all these sort of techniques that you use and libraries, they're all about layering things such that you're reusing someone else's code. But it took a while for people to structure that. The assess stage is the piece of this that is reusable by someone else. Because you might have a question in mind that is, how can I sell more of these, or how can I understand the nature of disease here? And you will have to do a bunch of work that helps you answer that question. But there's also a bunch of work there that everyone would have to do once they've got the data loaded up. And you want to make sure that you do that in such a way that someone else doesn't have to repeat. Yeah, so that's the assess stage. So normally in statistics, you might call this exploratory data analysis, this stage. But actually in statistics, even with exploratory data analysis, it's more that you have an understanding of why you've collected the data. This is an unusual and new thing, the idea that you should be doing things before you even understand why you collected this data. And it happens because, of course, nowadays we're just collecting data. It's so cheap to collect data. We're not actively collecting data. Whereas in the days of statistics, you wouldn't go out and collect data unless you knew what you were doing. Yeah. So I sometimes call that happenstance data because it's just around. And that contrasts very strongly with classic statistical data, which is known as surveillance data, because it's a statistical survey, different from surveillance data as in government surveillance, but that's the same term, surveillance data, statistical survey data, collected to answer a particular question, totally opposite. Finally, the address stage is now you're trying to answer the question you care about with that data. Was this drug effective? What is the label of this digit? Is there a cow in this image? Whatever, you're answering the questions. But notice we're keeping that separate. And that's where your machine learning, so there is some machine learning in here, but it's mainly sort of unsupervised learning and visualization techniques. Here, the address, that's where you might start using logistic discriminants, neural networks, whatever you're using to answer the final question. But in many projects I saw at Amazon, which is a very advanced data company, there was one project where a machine learner was recruited. It took them 2 years to get the data in a state where they could start addressing the question. 2 years. Okay. So like I said, work to make the data electronically accessible could include legal, ethical work, extraction data from where it's held. And I have this notion of data readiness levels that back this. So data that is not yet being accessed, I think of it as this readiness level C. And the reason I have that language is because if I'm talking to a manager about the state of the data we need, I want terms that the manager can go, oh, readiness level C. Oh, okay. So that like the next time when they hear something's data readiness level C, they have the instinct that that's a problem, right? So that I wrote a paper about that in about 2017. So here's my access case study. So these are two colleagues that worked in Kampala. This is Jimmy, and this is Mike, who was a postdoc with me in Sheffield. But before he came to Sheffield, he worked on this crash map, Kampala. And the idea was to try and understand Mike used to cycle to the university in Kampala on his bike. And if you cycle in Kampala, you probably do worry about car accidents. And he became curious, what is the biggest cause of death for young people in Kampala? Is it some form of disease? Because there's a lot of work on diseases. Or is it actually road traffic accidents? And there's sort of no way of finding this out. But these accidents were logged. So he built this system. This is a few years ago. So you would build it very differently today, much more capabilities, called Crash Map Kampala, where he was crowdsourcing people to sort of take the information from the logbooks and doing all sorts of work to keep the information private. So what he's done is some pre-work to make sure that you're only seeing the address and you're being asked to read the address, right? So this is, maybe we could do this quite quickly with some modern foundation model type thing, but this is like 2014, something like this. So his access is like even this crowdsourcing thing. And you imagine if you're doing a psychological study or whatever, and different logbooks from different places, recording in different ways with different notations, even that's going to be very hard, even with modern AI. And whether the accident was minor, whether it was a hit and run. Does anyone see what that's saying? Can you interpret what that is? You can probably if you look down here. Motor car. This would presumably be light goods vehicle. So, all stored in these sort of ways. Jimmy, by the way, the reason they could access this data is Jimmy worked for the Kampala police. Yeah, not that clear because someone's just written across the logbook, right? So, for some, this is an access thing. So to what extent can we automate this? Because we're trying to automate some of these things. Well, there's a lot of interesting tools around about now. If you knew a specific case, but it's going to be a lot of work to build the pipeline to reliably automate this, something like that. Indeed, one of the things you often find, and by the way, it probably would not be a good idea to give them a mobile phone app and say, why don't you record the data in this? Because the capability of the Kampala police to reliably store data in a digital form is probably way less than their ability to store it in logbooks. So if you give them a digital solution, you're probably going to you're effectively maybe destroying years of data, and it's conceivable we could reaccess this data in an analog form. So assess the things you can do without knowing the question. So my case study here is text mining for COVID misinformation. So this is Joyce, is another collaborator in Kampala, and she was trying to deal in COVID with supporting when fake news is being propagated on Twitter or whatever social media she was using. So there's really interesting challenges here because you can't use just regular language things. I mean, the language models of the time were worse than they were today. So this is being classified as fake, and it's Biogera language, right, which is one of the, there's multiple languages in Kampala. This is what's called code switched. So there's multiple things going on in terms of the languages switching. So it's quite common for people to speak a mix of English and their local language. And you're trying to classify fake information through that. So, but a lot of the project that is listed in the notes is going through the sort of things that Joyce had to do before she could start doing the classification, right? She's got all this data. The access wasn't such a big issue. Well, it's a big issue for Facebook, but for the data she had, she could access it off wherever she got it. But then once she's got it, she's trying to work to understand, how do I process this? What's in here? Is this code switch? What languages are available? All of this stuff. Even if you were doing sentiment analysis later, that would still be useful for you, right? It's not just about misinformation around COVID. It could be useful for all sorts of things. So there's a whole sort of assess stage. And then you build a classifier. Is this misinformation or not? Is it about COVID or not? So there's interesting projects. And again, I mean, I think we'll see a whole wave of new things in this space around LLMs, right? But this is going back before LLMs, a load of different work of trying to understand how to automate, assess, and then address is kind of what you expect to be doing in this course. What university courses are about. Like, here's a machine learning algorithm. This is how classification works. This is how regression works, right? And, we're not going to talk massively about it. We're going to have a couple of lectures on it. but it could be confirmatory data analysis, which in statistics is like a randomized controlled trial followed by a conclusion being drawn. A machine learning prediction model, a visualization through a dashboard. I mean, that's very useful, or sort of the right form of clustering for a biologist to understand what's in their data. And it could be an Excel spreadsheet. That was something that we ended up doing at Amazon quite a lot. You would have this pipeline of analysis, and then you would give an Excel spreadsheet of the summary statistics to your vice president because they knew how to use Excel, right? And then they could play with the analysis and come back and say, what's going on here, right? That's really, really important because it's giving people back that sense of how we like to interact with the world. We can poke things. And that's why Excel's so successful, right? It's easy for people to poke things in Excel. It's a nightmare from a classical computer science perspective, but it empowers normal people. Okay, so there's some other things around that. And we're giving you a Fynesse template in the, which is a very simple template just for you to get started so that when you're actually programming, you're thinking about which bits of your code to put under access, which to put under assess, and which to put under address. And yes, it will be the case that some stuff isn't clear. That you're thinking, wait, which one of these is it? And I think that's the interesting bit, right? Because now you're seriously thinking about your processing pipeline in the way of its reusability. I'm not saying this process is perfect, right? It's something we made up to try and capture these ideas. Nearly done. So final 30 seconds. LLMs, what's going on? Well, despite the fact that these are nothing to do with human intelligence, we've built machines that have a view of the world that is analogous to ours. Because we told these machines, play this game of predicting the next word. And in order to play that game really well, they looked at 300 million times more data than we could ever look at. And in order to play that game really, really well, they gained some cultural sense. Not in the way we gain it, but they have concepts inside the machine that are analogous to states inside our head. And this is an amazing change, because what this means is there's a new node in this graph. And this new node is of the following form. There is psychology between us and the data science, right? And that's exciting. And that's going to change everything. And you're going to be there while that happens. There'll be bits of that in this lab, but we can't teach that yet because we don't know what it's going to look like. A totally new interface to the machine. And so with that, I'll end there. We'll be outside for a bit so you can ask me questions. And sorry for having to rush through. Okay, thanks very much. Sorry, on you go.